Alkynes, properties, preparations, and reactions. Èmi ò gbọ́ nǹkan kan. Should be. Is course prep available online? Good evening, class. If course prep is available, let him indicate. Abam Solomon, are you the course prep?
No, ma. It's Giwa Ibrahim.
Who?
Giwa Ibrahim, ma.
Are you the assistant?
No, we don't have assistant. We don't have assistant.
So the course rep is not available yet.
Maybe we will soon join. Some people will do experience network issues before they join.
So you're going to control the class for me today. I've made a co-host.
Okay, ma.
As soon as it's 8:30, we are going to start the class.
Okay, ma.
Mr. Abang, mute your mic, please. Mr. Abang, Solomon, please mute your mic.
District church. They'll be taking it every
Apologies, I think I lost network on them. I've been battling with it. Okay, let's quickly go into what we have today. So in today's class, we're going to talk about alkyne. We've talked about alkane. We've talked about alkane. Today we're going to deal with alkyne. Remember, these are hydrocarbons, meaning they are compounds that contain hydrogen and carbon. Today's class, we're going to look at the properties, the preparation, and the reactions. Remember, I said that this is not going to be as long as that of alkanes, because virtually we are repeating what we did in alkanes. We're going to see most of them in alkane. In terms of reaction, difference between alkane and alkyne is that even alkane needs 1 mole, alkyne needs 2 moles of reagents for reaction. So introduction, alkynes are hydrocarbon, like I said. They have 1 carbon-carbon triple bond, meaning that the homologous series starts with carbon number 2 because it takes 2 to form a bonding. So the most simplest of alkyne are ethyne, which is called acetylene. Okay, when carbon is 2. And from what we've learned so far, their hybridization is sp. And I said their character is 50% S character and 50% P character. Okay, meaning when you are talking about triple bond, meaning that it has 1 sigma bond and 2 pi bond. 2 pi bond makes it to be weaker than alkane that has 1 pi bond. Okay, making it to be more reactive than alkanes that has 1 pi bond. The weaker, the more reactive. The stronger, the less reactive. Okay, this is the bond angle. Looking at the structure, you can see that it is linear on a straight line, which brought about the 180 degrees bond angle. So the structure geometry is linear and the bond angle is 180. The hybridization is sp. Okay, like we saw in alkanes, alkyne can have terminal and internal alkynes. Like we also saw in alkane, terminal are not as stable as internal. And the general molecular formula for this alkyne is CnH2n-2. Remember, in alkane, it is CnH2n plus 2. In alkane, it's CnH2n, while in alkyne is CnH2n-2. The -2 is what brought about the additional double bond. So in terms of saturation, alkane are saturated, alkane are unsaturated, alkyne are super unsaturated. Okay, making them more reactive because the more unsaturated, the higher the reactivity. In terms of naming, like we name alkanes the same way we name alkyne. So the A of alkane is replaced with Y. Alkane, alkyne. So whatever you're naming, you end it in yin. Unlike in alkane, you end it in in. So the same method of naming in alkane is still available here. What changes is that the family compound is no more in, is yin. So this example, you can see that my triple bond is on carbon number 1. I'll call it 1-butyne. I can call it but1 yin. Co-host, please, you're supposed to be muted. I'm hearing noise. Albums, you must be muted. Everybody must be muted. Okay?
Yes, ma'am.
I'm waiting for you to mute yourself, Albums.
Yes.
I get what I say, no busy for call.
Where is Abam Solomon? Is he in the class?
I'm trying to mute myself.
Abam Solomon.
Yes, ma. I am trying to mute myself. It's not going.
Abam Solomon, mute yourself.
Yes, ma. That's what exactly I'm trying to do. Let me leave this place.
Please, anybody that I see that is not muted, I'm going to remove the person from the class myself. I'm warning the last time, Charles Benedict, you're not muted. And your video is on. I don't have any issue with your video. But if you're not muted, in the next 5 seconds, I'm going to take you out of the class. It means that he's not in the class.
Yeah.
Tell him I don't need people like that from class. Charles.
Yes,
Don't dare me.
yes, ma.
See, anybody I remove from this class will not participate in my class again. I don't like distraction.
Sorry, ma.
If you look at this slide, I want to focus on the strokes or lines. When you have a compound like that, wherever you see the triple bond, there are 2 carbons that is connected by that triple bond. So where you saw that triple bond, there are carbon that started it and carbon that ended it. So that is why the total number of the carbon here is 10. That's why we have it, the kind. And starting from my own right, the carbon number 4 is what is bearing the triple bond. So that's why we have it for the kind or dec for yin. So the first one is 1 pentyne is very common, is understandable. Then the other one is a cyclo compound. This cyclo compound has an extension which is aliphatic. Now, because the cyclo is more in number of carbon than the aliphatic, so we're going to name the compound as a cyclo, and the straight chain is going to be a substituent. Now, looking at that, we know that I'm going to consider my triple bond when naming. That's why the place where my substituent is on carbon number 3, following the position of double bond. Okay, now my substituent is boots, carbon number 4, making it boots. And in that boot, we have double bond and carbon number 2. That's why we call it butylene, because it's not a substituent. So we have 3. The position of this butylene is 3, and the compound is cyclohexane. Cyclohexane. So that's why we have 3 hyphen bracket 2 butylene, then cyclohexane. Looking at the last structure, we have both double bond and triple bond. In that case, triple bond has priority is going to be the parent, while double bond becomes a substituent or become a washing. In that case, I'll start naming, giving my triple bond so I'm going to name, starting from giving my triple bond the priority as a parent compound. So I'm starting from carbon number 1. You can see my 1 is where my double bond is. 2, 3, 4, 5 is where I have a phenyl, and 6 is where I have the yin. So being the parent compound, whenever you want to give your name, they say I am David Mark. David is my name, Mark is my surname. So Mark come first. So that's what we employ in this naming. So that's why we have 5 phenyl, because phenyl is at number 5. 1 heptene, because double bond is at carbon number 1. Hept is the total number of the carbon. Then 6 is where my triple bond is. So I can call it 5 phenyl hept 1 in 6 yin. That can also be named that way. You guys are daring me. Anybody that hear the voice, whether you muted later, as long as you distracted me, you leave the class. And I mean every bit of it. Now we'll talk about isomerism. Isomers, like I said, are twins. So when you talk about isomerism, you talk about existence of you talk about a compound that can exist as twins. Okay? In alkyne, isomerism can start from the third member. Remember, the first member is 18, second member is propene. Okay? Then the third member is butane. So for me to have isomerism, it can only start from but. Yes, whenever you want to name, you start naming from the double bond, but the compound is going to be named as a parent compound of triple bond. So the triple bond will be last, double bond will be first. Okay. So whenever we are talking about what we are going to have is chain isomerism. We can have position and we can also have functional. No, functional isomerism is not always feasible, except because when you're talking about alkyne, we can only have chain and position. And functional group is not always feasible because it does not change the functional group of the compound. So anything that happens in alkane happens in alkyne. What we can talk about functional group isomerism is when you have a saturated compound. As in this case, except we are having a compound that has functional group like hydroxy group. But whatever that happens, the isomerism that is very, very prominent in alkene and alkyne are chain and position. Note that. Okay, this is straight chain and branch chain. That's a typical example of chain isomerism we can talk about. Okay. Then if you talk about position isomerism, you can talk about having but 1 and but in. That example of position isomerism. Note that the change of position of the triple bond changes in identity of the compound. Okay. Okay. So physical properties of alkyne. Now, this alkyne resemble alkene of similar molecular weight. They have low melting point and boiling point. Just like we talk about alkanes, their melting point and boiling point increases as carbon chain increases. They are soluble in organic solvent and insoluble in water. They are not soluble in water. Okay, so these are the physical properties we can look at. This is ethene, this is propane. And if you look at their physical properties, you can realize that the more the carbon chain increases, the lower the melting point. But when you come to boiling point, the more the carbon chain increases, the higher the boiling point, right? Okay. Now, but look at what happens. If you look at pentine, pent 1 in, and look at but 2 in, you can realize that my but 1 in has 126 and my but 2 in has 32, meaning that but 2 in has higher boiling point than but 1 in. Then look at 1 pentane and hexane. So you can realize that my hexane, okay, is 132. 1 pent is 90. Now, from pent to hex, there is a lower, because the more the negative, the lower. But in boiling point is increasing. Okay. So that's what another thing can talk about in their physical properties. From the melting point, you can understand that the position changes. So now, what are we talking about? If you look at 1 butane, you realize that it is terminal double bond, making the boiling point to be what? Very low. And this one is balanced. Okay, but 2 in is more balanced than but 1 in. So the more the balance, the higher the melting point. Because this one is unstable already. Okay, so it can easily melt because they're already unstable by virtue of having a terminal triple bond. Here is unstable. So anyone that has terminal is unstable, and they will have lower melting point than the one that is balanced. So the same thing with the boiling point. The preparation. The most important preparation of this alkyne is from calcium carbide. So calcium carbide will react with water to form calcium hydroxide and ethylene. That's a smallest one. Okay, but nobody will ask you this in exam. So what you're going to focus on in this is the reactions. Is a reaction of alkyne. Like we talk about addition reaction, we talk about addition of hydrogen, addition of halogen, addition of hydrogen halide. Okay, so this is what we have here. Whenever I want to react, do addition of, now SH is when you are doing hydrogen halide, because X and H are not similar. So whenever you want to add compound that are not similar, like HX, okay, that's a hydrogen halide. The method you're meant to employ on the first step of the, remember you need 2 moles. On the first step of the reaction, anything can go anywhere. You can add anything to anyone. But after then, on the second step, you can employ Markovnikov's rule. Okay. I don't know whether we'll talk about Markovnikov's rules in the previous class. Markovnikov's rule is even talking about that whenever I want to add a compound that are not similar across the double bond, the carbon that have hydrogen will be given hydrogen. The carbon that have less hydrogen will be given the halide. So that is what we employ whenever you're doing the second stage of the reaction. I don't know whether we'll finish alkane in the reactions of alkane. So if we did not finish it, please let me know. Okay, this is halogenation of alkane. This is hydrogenation of alkane. Hydrogenation of alkane is the same thing in alkane because it's hydrogen. So I can add my hydrogen in any of the carbons. It does not matter because they are similar. So the only thing I need to consider is that my hydrogenation must go with a catalyst. The catalyst can either be platinum, palladium, nickel, or rhodium. So these are the catalysts. So remember, because alkyne has triple bond, I'm going to need 2 mole of hydrogen. Unlike in alkane, I'm going to have just 1 mole. Okay? So this is now, but whenever I'm doing addition of hydrogen halide, it's a different ballgame entirely. The first stage can go without anything. You can, because the compound are symmetrical. When a compound is symmetrical, it means that when I divide them, I'm going to get equal half. So for symmetrical compound, Markovnikov's rule does not play. But when a compound is asymmetrical, meaning that when I divide them, I cannot get when I divide them into 2, they cannot give me 2 equal half. So they will be dissimilar. Because they're not the same, I will employ Markovnikov's rule. Like I said, the Markovnikov rule says that whenever I want to add hydrogen halide across a double bond, the carbon that is connected by the double bond is what is reacting. So that carbon that have more hydrogen, I'm going to give that carbon hydrogen. The carbon that have less hydrogen will be given the halide. Okay. Now, if you look at the reaction under, you can see that when you divide this compound into 2, I'm not going to have 2 equal. So if I want to react this compound, I'm going to employ Markovnikov's rule. In that Markovnikov's rule, the carbon that is the second carbon, which does not have hydrogen, is going to have halide. And the first carbon, which have only 1 hydrogen, is going to have hydrogen. That is why we have this, employing Markovnikov's rule. But remember, from this now, because it is asymmetrical, that's why we're going to employ it. Then in the second section, we can also realize that it's still asymmetrical. So I'll go further to also employ what I did by giving that carbon, that second carbon, halide, and the last carbon, hydrogen. So whenever you want to do hydrogen halide, consider whether the compound you're doing is symmetrical or asymmetrical. If the compound is symmetrical, Markovnikov's rule does not apply. It only applies when a compound is asymmetrical. I hope that is well understood. Okay, look at this compound is asymmetrical. That is why I have to employ Markovnikov's rule in forming the product. Okay. Now, because remember, alkyne they have triple bond. So in terms of reactivity, they have to react twice, while alkanes have just 1 bond, double bond. So they can react faster than alkane. But in alkyne, they need more moles of reaction to occur, but alkane need less. So in terms of alkane are slightly less reactive because they have so many unsaturation. So before you fill them, you have to go extra mile. So that's why they're slightly less reactive. Now, whenever you see a compound that has hydrogen halide and there is peroxide, it's telling us that this is going to be opposite of Markovnikov's rule. So it is anti-Markovnikov's rule, meaning that in that case, the carbon that have less hydrogen is going to be given hydrogen. The one that has more hydrogen is going to be given halide. Remember, in Markovnikov's, the carbon that have less hydrogen are going to be given halogen. But in anti-Markovnikov's, the carbon that have less hydrogen are going to be given hydrogen. Please understand that very well. So whenever you see a reaction and you're giving hydrogen halide and the reaction compound is unsaturated and you're expected to form a product, as long as there is hydrogen peroxide, either they write it as peroxide or they write it as H2O2, the same thing. It means that you're going to work with anti-Markovnikov's, meaning the carbon with more hydrogen will be given halide, the carbon with less hydrogen will be given hydrogen. Please understand this Markovnikov's. So this is halogenation. In halogenation of alkyne, you don't need Markovnikov's rule. Remember, in hydrogenation, you don't need Markovnikov's. In halogenation, you don't need Markovnikov's. You only need Markovnikov's when you're doing hydrohalogenation. only hydrogen and halide. That's when you need Markov-Nikovs. So in this case, because I'm halogenating, I can add my chlorine anywhere. It does not affect anything. So ask I think this is the end of the slide. Ask your question on this. I think I want to go back to alkane. I don't know whether I will finish alkane. I want to get a feedback from class. Did we finish alkane? So we can go to benzene. Did we finish alkane? Somebody should talk to me. Did we finish alkane?
Yes, I think we did.
I hope you guys were seeing the slide. Were you seeing the slide?
Yes, we are seeing this live.
Eh?
That is so
Yes,
small.
Yes, ma, we are seeing the slides. We are seeing it.
Hello, Pastor.
You saw the slide when I was talking. Did you see the slide?
Yes, ma.
Okay, fine. Okay,
Yes,
fine.
We
ma.
saw it.
So we have finished alkane, Abi. So we can go ahead and do benzene.
I don't think we talked about the chemical properties of alkane.
Because I was trying to remember if something like that was talked about. Okay, so let's see if we can go back there.
Ooh.
Which one is this one? Okay. I think we did all this. I think we did this. Please, I need a confirmation in the class, in the house. I think we did this, right? And we talked about the preparation, right?
Yes, ma.
Did you talk about the preparation?
Yes, we did, ma.
Yes.
We talked about the preparation.
Yes,
Okay.
ma.
Okay. Did we? But have we started this hydrogenation, the reaction?
No.
Okay. I think let me start from here. Let me start from here.
Yes.
Now, with what I'm going to say now is you're going to be familiar with it because of what we talk about in alkane, in alkyne. So, addition reaction, like we did in alkyne, the same thing with alkane. The same thing we said, addition of hydrogen. You don't talk about where you're adding it because hydrogen is the same thing. What you need to do, you need to put the catalyst, okay, to do your hydrogenation. So the same thing happened here. This is just telling you the story. Okay, now let's talk about the addition reactions of alkanes. You're talking about hydrogenation, hydrohalogenation, hydration, halogenation, halohydrin, and hydroboration. Now, whatever that happened in the ring happened in the straight chain. If you look at the double bond that is going to break. Now, when this double bond breaks, it's going to give us electropositive and electronegative as carbocation and carbanion. And anything you're going to react with, you're going to divide them into carbocation and carbanion. So HX is going to break. Hydrogen is positive, halogen is negative. So that's how you're going to add them. Then water is going to break into hydrogen ion and hydroxyl ion. Then when two halogens are going to be broken, one is going to be the carbocation, one is going to be the carbanion. Okay. Now this one is halogen and water, meaning I'm going to have hydroxyl ion and I'm going to have halogen. We call it halohydrin. Halohydrin, if it's halogen is chlorine, it will be chlorohydrin. If it's bromo, it will be bromohydrin. Then hydroboration is when you're going to have boric acid in the presence of hydrogen peroxide and hydroxide. Okay, the hydroxyl group is going to, the bond is going to break. In that case, in this case, in hydroboration is only water we're going to add. Okay, but the difference between hydroboration and hydration is because of the reagent. Hydroboration is oxidation reaction. Okay, so that's just the difference between them. So you should be able to know at least 3 of these reactions. At least 3 of them. If you don't, the 3 of them, without looking at this, you should be able to know hydrohalogenation. You should be able to talk about halogenation and hydrogenation. Hydrogenation was not stressed here because it's a simple one. When you hydrogenate cyclohexane, you're going to have, when you hydrogenate cyclohexane, you're going to have cyclohexane. It means that the double bond will go. You're not adding anything at the end. It will just be a ring standing on its own because the double bond has been removed by addition of hydrogens. So we are in this place, we're going to talk about how do we add hydrogen halide. Like I said, when we're talking about alkyne, then when I have something like this, now look at this example. This is my 18. If I divide them into 2, I'm going to have 2 equal parts, making them symmetrical. When a compound is symmetrical, it means that I can divide them into 2 equal parts. In that case, I don't need Markovnikov's rule. Remember, whenever I'm dealing with hydrogen halide, I'm going to employ Markovnikov's rule. Because in this reaction, the compound I'm dealing with as symmetrical, I don't need Markovnikov's rule. So I can add my hydrogen anywhere, and I can add my halide anywhere. Okay? So in that same manner, when I have a cyclo compound, this cyclo compound is very symmetrical because they are at the center. So I can also add my hydrogen anywhere and halide anywhere. I'm going to form my product. But when I have a compound that is not symmetrical, that is when I talk about Markovnikov's rule. Now look at this compound, prop-1-ene or propene. You can understand that the first carbon have 2 hydrogen, while the second carbon have one hydrogen. In that case, if I want to add hydrogen halide, I'm going to employ Markovnikov's rule. The rule says that this carbon that have 2 hydrogen, I'm going to give it another hydrogen. The carbon that have just 1 hydrogen, I'm going to give it the halogen. So the rule says that, just like they said in the Bible, that the person that have more will be given. Okay? So that is why we're going to give hydrogen, carbon that have more hydrogen, another hydrogen. But the carbon that have less hydrogen will be given halogen. That is obeying Markovnikov's rule. Like I said, this is a typical example. The first compound is not symmetrical. Hence, Markovnikov's rule can play. You can see the carbon that have only 1 hydrogen was given the chlorine, while the terminal carbon was given the hydrogen as in product. But if you look at the second one, when you divide them into 2, they are still not symmetrical because one has methyl, the other one have hydrogen. So whenever I want to react, that carbon that have hydrogen will be given hydrogen. The one that does not have hydrogen and have methyl will be given halide. Now, but the last compound is symmetrical, meaning that if I divide them by the double bond, they are giving the same thing. So in that case, I can add my hydrogen anywhere and add my halide anywhere. So in that case, I don't need Markovnikov's rule for the reaction. So I hope we understood what Markovnikov's rule is all about. Like I said, in alkyne, whenever I have something like this and I have peroxide, that peroxide is telling me that this is going to be anti-Markovnikov's, meaning that the carbon that have the more hydrogen will be given halide. The carbon that have less hydrogen will be given hydrogen. That is anti-Markovnikov's orientation or arrangement. Whenever I have peroxide, like I said, this peroxide can also be written in formula. Like when I see that in my reaction, and that reaction is having hydrogen halide, it means that the orientation I'm going to employ is anti-Markovnikovs. But when I have hydrogen halide that does not have any peroxide, Markovnikovs will be employed only for asymmetrical compound. Symmetrical compound does not need Markovnikovs rule for orientation. Okay, now we're going to talk about polymerization. Like I said, polymerization is a process whereby many small and simple molecules called monomer join together to produce a very large molecules called polymer. Okay, that is what they call polymerization. Polymer are formed from monomers. So I think you should be able to understand what polymerization is, to be able to define it. Remember, it's a process. Polymerization is a process where small and simple molecules join together to form a complex or large molecules called polymer. So when you're talking about small and simple molecules, you bracket monomers. They join together to form a very large molecules called polymer. That's where we have our polyethylene. So this is ethylene now. Under polymerization, when so many ethylene join together, they are going to form polyethylene. So that's what we call polythene bag. So these are monomer of ethylene that join together to form a complex compound called polyethylene. So polyethylene is a polymer. Okay. Why the monomer of polyethylene is ethylene. I hope that is well understood. So in polymerization, we have types. We have addition polymerization, we have condensation polymerization. The difference between them is that in condensation polymerization, there is always elimination of molecules when functional group reacts. When they react, some molecules will be eliminated. While in addition polymerization, monomers are going to continue in addition form, okay, to form a polymer. They will be adding up. In condensation, they join together and let some things out to form a larger one. So unlike continuous addition we see in addition polymerization. So types of polymerization is addition and condensation polymerization. In addition, nothing is being removed. They are just adding up. While in condensation, two things come together to form a giant molecule, eliminating smaller molecules. Okay. So these are the common examples of addition polymers. The one that we talked about is polyethylene. Okay. We have polyethylene, we have polypropylene, we have polyvinyl chloride, and so on and so forth, as you can see here. These are all addition polymers. They come from addition reaction. And these are common polymers that we have that is very, very useful in industry, addition polymers. So let's ask a question. We'll be left with one class, which I don't want us to rush because this class is meant to end by 9:30. We wasted so much time. So in the next class, we just spend 1 hour. So I want you to ask questions on the reactions of alkane and alkynes. Ask question, anything you don't understand. The floor is there for you for the 10 minutes. So we can answer the questions and I joined the class for the last class. The highest number of alkane can be regarded as monomer. Let me read your question. Well, what's the highest number? I've told you, look at what we said. We said the simplest one is, we don't need high, the simplest one is ethylene. The simplest one is ethylene. So when ethylene combine, if you look at the last slide, what we're talking about polymer. So it's the things that combine that inspire the nature of the polymer. We have polypropylene, meaning that the monomers are propylene. Okay, the nature of the least simplest one is ethylene. So it can go as far as whatever, but the simplest ones we know. Okay, let's look at the last slide when we talk about the examples of addition polymer. So look at the polymers. Okay, vanillin chloride is the polymer. What you see is a polymer. Now polypropylene, the polymer there is propylene. Then polyacrylene nitrile. Okay, so all this is what in poly is many of it. So whatever that you're having after the poly, look at this vinyl acetate. It means that vinyl acetate, it is what is the monomer. So when I have so much of this vinyl acetate, I have polyvinyl acetate. So understand the word poly is many. So whatever that is becoming the poly is the monomer. Please, Ma, can you go over the concept of anti-Markovnikov's rule? And in what reaction does the rule? I've said it, anti-Markovnikov's rule is opposite of Markovnikov's rule. If you understand Markovnikov's rule, you understand anti. Anti is reverse. In Markovnikov's rule, the carbon that have more hydrogen is going to have the given hydrogen. In anti-Markovnikov's rule, the carbon that have more hydrogen is going to have the halide. Okay? That is it. Then Markovnikov's rule and anti-Markovnikov's rule can only apply when a compound is not symmetrical. Symmetrical compound is a compound that can divide into two equal halves. While asymmetrical compound are compound that can never be divided into two equal halves. Okay, you understood now. So, any other question? You
Yes,
can
ma.
unmute yourself and ask too.
Yes, ma.
Okay.
Firstly, sorry for joining late. Sorry for joining late, ma. It's because of the NEPA and light issue. Secondly, you were talking about symmetrical and asymmetrical. Can we also say that when something is when something is asymmetrical, can we say it's radially symmetrical?
A compound can either
Yes,
be
ma.
symmetrical or asymmetrical. I don't know what you mean by radially symmetrical. When a compound
Because in
cannot be
biology,
divided into two equal halves. What do you say?
I'm trying to chip in biology aspect of it.
Please,
Because in
biology and
biology,
chemistry, we are not the same, please. Don't bring biology here. We don't use
okay,
radially
ma.
in chemistry. We use symmetrical or asymmetrical in chemistry. Okay, if a compound is not symmetrical, it's asymmetrical. Okay, yeah. Lawal,
Noted.
Bidemi.
Good evening, ma.
Yeah,
Thank you very
Badmos, you're not muted.
Thank you very much, ma, for the class. Yes, ma.
Okay.
I from the chemical properties of alkene and alkynes that you mentioned, that you discussed about the Markovnikov's rule. Is it only applicable to hydrogen halides?
Yes, Markovnikov's rule is applicable to only hydrogen halide. When you want to react hydrogen halide across in a reaction that involves double bond or triple bond.
Okay. Okay, ma. Thank you, ma.
You're welcome. So, Kairat.
Yes, ma. Good evening, ma.
Good evening.
Ma, please, I want to ask in alkene, ENE, and alkyne, YNE, which one is more reactive?
In terms of reactivity now, alkene are more reactive than alkyne because for alkyne to finish reaction. Why am I getting echoes?
Ma?
Oh, I'm hearing myself. Can you mute yourself?
Okay, ma.
Okay, I think it's better now. So for alkyne to react, it has to just like telling yourself now. If somebody that is hungry and somebody that is not very hungry, who will get food fast? Somebody that is hungry, before the person get food, you would have finished all that you have. But somebody that is not hungry can easily be filled. Now, in terms of reactivity, alkyne needs so much to complete the reaction. So the process is longer than alkane. So that's why they said alkyne are least reactive, meaning that they are less reactive because I need 2 moles against 1 mole. So in terms of reactivity, alkanes are more reactive than alkyne. But alkyne need more moles than alkane. The ratio is 1:2. Any other question? Are you sorted? Kairat.
Yes, ma. Thank you, ma.
Okay, next question.
The next question, ma.
Excuse me,
Sorry,
Okay.
ma.
ma. This is Lawal again, ma.
Okay,
Yes, ma.
Lawal, go ahead.
When we are to name organic compound,
Yes.
we have both double and triple bonds on the same structure.
Okay. Okay.
Which one should we respect most between the two? Which one should be rather between the
Now,
two, ma?
like I said, triple bond is senior to double bond. So just like you, when you want to call your name, Lawal Abidemi, maybe assume that Lawal might be your name. Now, the first one, whenever you're giving priority in naming, you're going to name the parent compound as triple bond, but you're going to start naming from double bond. Do you understand?
No, really,
Because
ma.
you can't, so you don't count 3 without counting 2. So I have to name, giving my triple bond as a parent compound. So so I have to start from double bond and end in triple bond, both in numbering and in naming.
Okay. Let's say we have like pent 2 in 3 high.
Yes, because my 2 is double bond, my 3 is triple bond. So double bond will come before triple bond. So triple bond will end the reaction, will end the naming. Just like saying David Mark. Mark is a surname. So I start with the first name, I end in surname.
All right, ma.
So
Thank you, ma.
yeah, okay. Now another thing you can think about is if you talk about alphabetical order, you cannot talk about Y before talking about E. So that's why we talk about in before yin. Okay, Nkiru.
Good evening, ma.
Good evening.
In the reaction, the addition reaction, when we talk about addition of H2SO4, I didn't get that clear. I think it was water. Was it
Now, yeah,
a kind of a hydration reaction? The acid there is just to remove water or what?
in hydration, remember we are trying to bring out hydrogen ion and hydroxyl ion. They cannot come without a catalyst hastening the reaction. So the sulfuric acid is acting as a catalyst.
Okay,
Okay?
okay, ma.
Yes.
Okay, ma.
All right. Oyagiwa.
Okay, ma. Still on the question raised by Lawal Abidemi, talking about the single and the triple bond. So you said we
Okay.
should consider the double bond first.
Yes. Then
So
end up
mine
with
is
triple
now
bond.
when we have single bond and double bond, are we still going to consider the double bond firstly?
Single bond, if you want to consider single bond and double bond, single bond is something you don't consider at all because it's not a bond. Is a natural
Okay.
bond of a compound. Yes. So whenever you have
All
single
right.
bond and
So you go for
double bond is a functional group. We are dealing with when you have two
okay.
functional groups. Yes.
Okay, ma. Thank you, ma.
Yeah. Any other
Excuse me, ma.
question?
Excuse me, ma. Actually,
Okay.
when you were naming one of those compounds, you used the double bond as the parent name in one of the slides.
Yes. Double bond is a parent name if there is only double bond. But if you have double bond and triple bond,
So we have double bond and triple bond in the compound, and a
is
cyclo
it
in one
is
of the slides, ma.
is it on the alkyne slide or alkene slide?
Alkene slide.
Alkyne?
Alkyne, ma. Alkyne, ma.
Is it
Alkyne.
this slide or the previous slide? Okay,
The previous
let's go
slide,
to
ma.
that slide.
Alkyne.
Let's go to the slide. Now listen very well. In this cyclo compound, the alkyne section of this is a substituent. It's not the parent compound. It's a substituent. Whenever you're naming a compound, the substituent comes first before the parent compound. So that is why the substituent was being named first before the cyclohexane, which is the parent compound. It's different from this last compound where we have alkane, double bond and triple bond on a straight chain. Why the phenyl is a substituent. But this one now, my triple bond are substituents. Is a substituent here, while the parent compound is cyclohexane. They are two different things. So in this case, I'm naming because the carbon on the ring is more than the carbon on the straight chain. So that is why my straight chain become a substituent. If you look at this compound, the carbon on the straight chain is higher than that of the ring. Abi, this is hept, this is hex. So that is why the carbon on the ring become a substituent, while the straight chain became the parent compound. And you realize that in this compound, my double bond and triple bond are on the same compound that is straight chain. Unlike this, my double bond is on the cyclo compound, while triple bond is on the straight chain. And that straight chain has lower number of carbon, making it a substituent. So you cannot name a parent compound before substituent. It cannot work. So you have to name substituent first, irrespective of the nature of the substituent, whether it has double bond or it's just normal substituent like halogen, methyl, or whatever. You must give substituent priority when substituent is lesser than the parent compound. But when so now whenever you have two things on a compound, the one that has highest number of carbon becomes the parent compound, and the other ones are substituents. So that's what happens there. Did I answer your question?
Yes, ma.
Okay. Any other question?
Sorry, ma. Yes, ma. This is Lawal again, ma.
Okay.
Sorry, I'm looking at this structure that you just talked about, ma.
Okay.
Yes, ma. Can we call the substituents there? Can we call it can we call it boots too high?
Remember, you cannot call it too high because it's a substituent. You cannot call alkyl to be alkane. Can you call alkyl to be alkane?
No, ma.
So it cannot be too iron because making it to be an alkyne. This one is an alkyne as a substituent. That's why we call it butynyl. That's why L is telling us that this is a substituent, is not a parent compound. It's a substituent. A substituent is not complete, it's losing one hydrogen. That one hydrogen was what was replaced with this cyclo compound.
Okay,
Because it's not complete. Yes, so it cannot be that. Any
Can we
other question?
can we reorientate it to be like but 2 enil?
No, sir. There's nothing like enil.
Okay.
Where can we get enil? Because it's now this is butyl. Remember, if I remove that YL, I'm going to add E to make it a butyl, right?
Yes, ma'am.
Yes.
But because it's a substituent, just like when I put alkane, ANE. When I want to put alkyl, what do I remove? I'll remove NE and put YL, alkyl. The same thing that made my alkane to become alkyl. That's what made my butyl to become butynyl. Because it's no more a compound, it's a addition, it's a substituent, which is
Okay.
incomplete compound. So that is what you need to know.
Okay, ma'am.
So if it's double bond, where I have Y, I'm going to have E. It will become enil.
Okay. Because I'm just looking
Because
at the position of that triple bond on the
the position
substituent.
of the triple bond is what made it to be 2 now. The
I
position of the triple bond
understand.
make the compound to be normal. A normal compound of that is a 2 butyl. That's when it's a compound. This is a substituent. It cannot be 2 butyl again as a substituent. It's a substituent. It's not a compound. Any other question?
Yes, ma. Good evening. Please, the next
Good
class,
evening.
please come up with some examples of this similar nature. Please, ma. So
I don't
for a
understand.
better understanding. We need more examples on this this nomenclature, ma. So we can get a better understanding. This
Now I'm
the
giving you
cycle.
an assignment. Go online and bring out all the questions on the nomenclature. Name them and share with me. Then I'll tell you whether you're right or wrong. So go online. Look
Okay,
at nomenclature on alkene. Bring questions on that. Share it with us on the platform so we can do it together. Because I've given you what I need to give you, which is a clue on how to do it. So it's left for you to go and solve examples. Then share your examples and confirm if your naming is correct. That's how you learn. You learn by practicing. I must not be the one that will give you all the questions you practice. The only thing I can do at the end of the class, I can share some questions for you for the comprehensive course I've done for a questions like a revision question. But I cannot go and bring questions on nomenclature for you to solve. Which part do you have to do as a student? You have to also go and do more as a student. Then bring out your questions from things you've done and say, this one is difficult for me. This one is what I solve. Is it correct? Then I can affirm what you've done or correct you if you're wrong. So that's how you learn better. Okay, so I put it back to you. Go back and make more research and come back to me.
Excuse me, ma. What if we have our alkene here to be pentene?
Listen, as long as the straight chain, anyone that is more becomes the parent compound, the other one becomes a substituent. Just know it that way. Whenever you're given a compound to name, and there are 2 sides of that compound, the one that has the highest number of carbon becomes the parent compound. Other one becomes substituent. So go and look for questions and try and solve it them. Then you can share them with us here.
All right, ma.
Yes, thank you, ma'am.
You're welcome. So I think it's next week, Monday. We're going to have the last class next week, Monday. So please, if you have any questions, go back to all the slides that we've done so far. I'm going to share the slide of alkene and alkyne if I've not shared alkene before now. Do you have the slide of alkene?
No, ma.
Do we have okay, so I'm going to share the 2 slides now with you. So go through it, study them very well, so that in the next class we're going to finish benzene aromatic compound. I'm not going to go into details on that. I just want to give you the elementary knowledge of benzene aromatic compounds. So, and that's when we're going to end the class.
Yeah.
So the next class is like supposed to be on Monday, the normal time, which is it 11 or 10? Was it 9 that we
10.
did before? 10, right? Oh,
10, 10.
okay.
Yes,
Aruna.
yes, ma.
Okay.
Yes, ma. The fourth compound, where we have the double bond and the triple bond, the 2 functional groups. We have considered as you rightly said, the triple bond is one of the priority. So the double bond is the substituent bond. So I want to know why
I did not say double bond is a substituent. I did not say. I said whenever you have 2 functional groups, one will be higher than the other. Triple bond is higher than double bond, meaning that triple bond will be named as a parent compound, while double bond is going to be like a child, not substituent. The substituent we have here is a phenyl. A substituent is something that is not part of the parent compound. But double bond, there are 2 functional groups. So the lower one will go first, then the higher one will follow. So that's what we are going to name, starting from carbon number 1, where there is double bond. And that's why we have 1 heptene 6 ion. Is that clear? You cannot count ion. You cannot count Y before in. Remember, whenever you're talking about naming, you talk about alphabetical order.
Yes, ma'am. Yes, ma'am. It is understood now. Thank you, ma'am.
Hello, ma. Hello, ma.
Piano, kí ló tún fẹ́?
Mr. Lawal.
She's no longer in the class. Are we true?
Oh yeah, Mr. Abam, continue now.
As in the host now, yeah, continue.
Mr. Lawal.
Yes, ma'am.
Yeah, check out that last diagram. She started counting from in instead of ein. Did you notice?
Yeah, I noticed that.
Is it okay?
It's not supposed to.
Yeah, exactly.
When are we starting our tutorial guide?
Is that going to be online or in person at the center?
Mr. Abam Solomon,
Yes.
I think you end the class.
Okay.
Doctor is in. Doctor is in, please. Doctor is in. No, she's back online, please.
Okay.
Please, class, doctor is no more in the house. Can we log out now? Mr. Abam, you are the host today.